Lesson 121. Here are two lines, L and M, that are not parallel, that have been cut by a transversal, right? L and M, right? These two have been cut by a transversal. Tyler thinks that EBF is congruent to angle BCD. EBF is congruent to BCD, right? This angle here and this angle here. And because they're corresponding angles, and a translation along the directed line segment from B to C would take one angle to the other. This is his claim. He thinks that if you slide this angle right here down this line, that it will match up perfectly with this angle right here. And here's his reasoning. He says the translation takes B onto C. So B lands on C. Okay, great, no problem, right? The translation takes E somewhere on ray CB because it would need to be translated by a distance greater than BC to land on the other side of C. Meaning, if I slide E downwards by a distance of B to C, it can't end up on the other side of C. It has to, because it's on the top side of B, it has to be on the top side of C. That's all. Okay? And since we're sliding right down this line, it's got to land on there somewhere. All right. The third thing he says is that the image of F, this point right here, after you move it, has to land somewhere on line M, on this line right here. And he says, because translations take lines to parallel lines, right? When you move a line, it'll end up creating a parallel line, right? And he says that M is the only line that's parallel to L that goes through B. Or B prime, excuse me, which is going to be C because B is now B prime down here. Well, that's wrong, right? Because right here it tells us that they are not parallel. They're not parallel, okay? So sure, it'll take this to a parallel line, but this is not parallel with that one. L is not parallel to M. So when we slide L down, it will not be parallel. It will not land on M because M is parallel. M is not parallel to L. I'm getting my letters mixed up. Okay. All right, cool. So last statement, the image of F, call it F prime, has to land on the right-hand side of BC, or else the line from F to F prime wouldn't be parallel to the directed line segment from B to C. Now, we did a whole thing where we connect dots when we do translations, and there were all these dots all over the page, and we ended up with some parallel line segments because we translated them. And so if we're sliding things using B to C, then F to F prime also has to be parallel to our BC vector that we're doing, right, from B to C. If we slide F from here down and we use this as our direction, then it's got to be parallel to that direction. So that I don't have a problem with that. It also says that F prime has to end up down here somewhere on this side of the line. It will not cross over this line. It will not cross over and land on this side of BC because, well, duh, we're not reflecting it. We're just translating it, right? Okay, so obviously our third statement is the problem. And the basis of that is that he says that it's parallel, but it's not parallel. So there's your problem right there, all right? So in what circumstances are corresponding angles congruent? Well, if these two lines were parallel, then he would have been right? Tyler would have been right because this line AF, or line L, going across this way, and line M would be, if they're parallel, then sure, you slide this angle down and it'll match up perfectly because the orientation, the angle didn't change. Okay? All right. So next one, use the applet below to create a triangle. Okay, here we go. I'm going to create a triangle. One, or A, B, C. There's my triangle. Okay, then it says mark the midpoints. Oh, I labeled the interior angles as A, B, and C. Okay, I'm just going to move these so that they are on the inside here so that we can say, oh yeah, That angle right there is angle A, B, and C. Okay, there we go. All right, mark the midpoints of the two of the sides. Okay, so marking the midpoints, I'm going to use this midpoint or center tool. So if I click on this edge, it will find the middle of that, and I can click on this edge and find the middle of that. Okay, so right in the middle of that line segment and right in the middle of that line segment. It says, oh, extend the side of the triangle without the midpoint in both directions to make a line. Okay, so this is the one without the midpoint, so I got to extend this in both directions and make it into a line. I can do that. There we go. Use what we know about rotations to create a line that's parallel to the line that we just made that goes through the opposite vertex. Remember, opposite vertex, that's the corner. Vertex is the corner of an angle or the corner of a polygon. So we want a parallel line to this one that goes through that point B. And it says that we can do some transformations. We know that if we rotate this line around any point that is not on the line, and we rotate it by 180 degrees, it will end up exactly parallel to where it started. Now, for this one, I used D, but I could just as easily have used same line, but used E as that as the point, the center of rotation, excuse me. And again, 180 degrees. Bam, still I'm going to end up on B. Okay, great. All right, so now I'm looking at this. I'm like, all right, kind of a weird diagram, but okay. Then it says, what is the value of A plus B plus C? Explain your reasoning. Okay, so A plus B plus C. Well, we know that these are parallel. And we know some stuff about parallel lines and if there's a transversal. Well, isn't this a transversal? A, B, isn't that a transversal? Well, yeah. And we know that when we have a transversal, right, if you can imagine this going on forever, right, there's your transversal, that alternate interior angles are the same, right? If they're on the inside of the sandwich and they're on either side of the toothpick, opposite sides of the toothpick, they have to be the same, which means that this angle here, angle A, and this angle up here have to be the same. So I'm going to put another A up here. Boom. Okay. And we'll move that over so it's right in there. There you go. So that's angle A right there. It's the same as angle A down here. Okay. Actually, can I edit that? No, I can't. Okay. All right. So now there's angle B. Well, I can also look at this as a transversal, right? I can look at BC as a transversal also. And I can go, hey, look, this angle has to be the same as this angle because of alternate interior angles. So that means that angle C down here is the same as this angle in white right here. So I'm going to put a C right there. Okay. Cool. So, okay, it's being annoying. There we go. Okay. So I'm going to get rid of this line here. There we go. All right, so look, can't we just look at this and go, wow, A, B, and C added together are the same as this straight line right here. And we know that the measure of a straight line, because it's half a circle, is 180 degrees. So that is what goes here, right? Your explanation of why this A plus B plus C is equal to 180 degrees. There you go. All right, so now it says use the same applet above. We're going to do some other stuff here. It says translate ABC, triangle ABC, along the directed line segment from B to C. Okay, so we'll do the translate by vector. take the triangle. We're going to go from B to C. Okay, there it is. Okay. And now, so I'm going to also move these because this is actually B, right? Those are the angles on the inside. I'm just moving them to the inside so that we can see that they match up, right? Because this triangle got moved down here, so A, B, B, C prime, C, right? B prime, B, A prime, A, right? They match. Okay. Then it says, translate triangle A prime, B prime, C prime along directed line segment from, now this should say from A prime to C, not A prime to C prime. Okay, so I'm going to translate by vector, translate this from A prime up to point C, which is right here. And now we've got this. Okay, and I'm going to, once again, I'm going to move these letters so that they're on the inside of this triangle. This is the corner with A prime. This is the corner with B double prime, excuse me, and C double prime over there. All right, cool. So now we're looking at this. We got, hey, I have a straight line here, don't I? It says, label the measure of the angles that meet at point C. Well, point C is right here because this is one of our original points. Doesn't have a prime next to it. So, okay, well, this one is the measure of angle C. This is the measure of angle A because we just translated this thing down and then up. Could have translated it over too. Doesn't really matter. So this angle here is the same as this angle here, right? Angle A and angle A double prime are the same. We're just missing this piece right here. This piece in white, this angle in white. But as I look at it, I'm going, it kind of looks like, isn't it the same as B? Because look, don't these make an X? And isn't this a vertical angle right here? This is actually a vertical angle for B, or B prime, right? So I can actually label this and put a little B in here. This is actually angle B, right? And once again, if we look at this line that goes along this part here from A to C and C prime, don't I have angle A prime, or angle A, the same thing as over here, angle B, which is the same as down here, and angle C, which is my original angle C. Ta-da! Those three are also going to add up to 180 degrees. Well, there you go. There's the answer to that one. Okay? Right? So this white angle has to be the same as B prime because they are vertical angles. That would be the response here. Right? Okay, so one reason mathematicians like to have rigorous proofs even when conjectures seem to be true is it can help reveal what assertions were used, right? What assumptions? What are you assuming when you're coming up with your statement? So this is going to open up new areas to explore if we change those assumptions. For example, both of our proofs that the measures of the angles of a triangle sum to 180 degrees were based on rigid transformations that take lines to parallel lines. If our assumptions about parallel lines changed, so would the consequences about triangle angle sums. In other words, how the angles add up in a triangle. Any study of geometry where these assumptions change is called non-Euclidean geometry. Euclid was a famous mathematician. Okay. In some non-Euclidean geometries, lines in the same direction may intersect, while others do not. In spherical geometry, which studies curved surfaces like the surface of the Earth, lines in the same direction always intersect. This has amazing consequences for triangles. Imagine a triangle connecting the North Pole at a point on the North Pole, a point on the equator, and a second point on the equator 1/4 of the way around the Earth from the first. What is the sum of the angles of this triangle? Well, the crazy thing is that that's definitely above 180 degrees. In fact, it's 270 degrees. Why? Because, well, take a look at a globe or a basketball, and you'll be able to figure it out. All right, head off to work on the practice stuff. All right, see ya.